Hi students, Professor Gray here. We need to talk about buffers. So on the first slide, you guys can see we've got some health and beauty products here. And back in the 80s and 90s, there used to be secret commercials that would say strong enough for a man, but pH balance for a woman. And everyone just knew that was their ad and never thought a whole lot about what pH balance was. And this is something that is typically used in health and beauty aids to advertise different products, but not many of us give it a whole lot of thought. So, what on earth are they talking about? Well, there are different physiological pH values around our body. So, for instance, the skin is acidic, so it has a pH value of 4.5 to 6. So, if we have deodorants or lotions or soaps, we don't want the pH of those products to be incredibly out of whack or disturb the pH balance of our skin, because our skin has that pH because it functions best there and it kills microorganisms that need to be killed or lets the ones live that need to live. So yes, it's very important that the products that we put on our skin aren't going to burn us or do something else to us. Now, we also need to take a look at the pH of blood. So we can see that it is 7.35 to about 7.45. So blood is a little bit basic. And it's super important that we keep the blood right around that pH, or else it really messes with us or it kills us. And we're going to come back to the blood's pH in a little bit. But first, just take a look at the picture there, and you can see that we've got a very acidic stomach, and that's really important for killing things that might make us sick and also starting the digestive process of proteins. And then once we dump the stuff from our stomach into the small intestine, we can see it goes from acidic to basic when we get into the small intestine there. And there's a few others on here that are a little bit of an interest. So we can see saliva is usually 6.0 to 7.4, so pretty neutral there. Again, the blood is a little bit basic. You can see that in all of those different types of blood, or blood in different parts of the body. Skeletal muscle, pretty neutral until we get to exercising, and then we dump a bunch of lactic acid in there and we're like, now we're sore the next day. Okay, so how do we keep these pH values stable so we don't have problems around our body? Well, the body's pretty good at that, and it uses different buffering systems. But first, what's a buffer? Well, a buffer is a substance that's going to resist a change in pH. So it helps out the system by keeping the pH pretty stable. And usually it can keep the pH stable when there's an addition of a little bit of acid or base. But obviously, if you overwhelm the system with acid or base, then the pH will change a whole lot. So let's take a look at with and without a buffer. So if we have some water, so pure water, we've got a pH of 7. And then if we add an acid into that water, what we'll see is that the pH will drop. So you can see on the pH meter right there, we have a drop to 1.7. So that's very acidic. If we add base to that water, we'll see the pH increase because basic systems have a pH above 7. Now, if we add a buffer into the system, we would expect the pH not to change as much as it did in the above picture. So we can see here that we have a buffered solution. So it starts at about pH of 4.74. And if we add a little bit of acid in it, we can see that the pH decreases a little bit, which is what we would expect if we added acid, because remember, acidic solutions, we've got a pH from 0 to 7, so it's the lower end. And if we add a little bit of base, the pH goes above the original 4.74 to 4.77. But those two values, 4.70 and 4.77, are so close to 4.74, you can see there's something there that's resisting the change in pH like we saw in the above pictures when we added the same amount of acid and base. So what is a buffer in terms of chemicals? Well, the first example that we have is a weak acid and a salt containing its conjugate base. So the acid that we have here is HCN. Okay, so hydrocyanic acid. And hydrocyanic acid, being a weak base, doesn't ionize or doesn't dissociate in water very much. So we have some HCN floating around amongst a lot of water molecules. So we have billions and billions of water molecules in here. And then what we're going to have is we're going to have a few, and let me change over to a different color. We're going to have a few of these and a few of these, but not very much, because remember, this one right here is a weak acid, so it doesn't dissociate very much, so very little. So we get very little of this and very little of this. And what we're looking for in this system here is the weak acid right here and its conjugate base, so this right here, but we don't have very much of the cyanide ion. So what we need to do is we need to add a salt that contains that anion, and the salt needs to be very soluble so it dissociates, or it ionizes a whole lot, so we're dumping a lot of cyanide in there. And the salt is this right here. We have sodium cyanide, and that's very soluble. So you put it in water, and if I were to be really picky, I would put AQ, 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 just so you know that it's floating around in water and not oil. And those things will also be in your beaker with the water molecules and the other molecules, the other ions and molecules. Okay, so we have Na, and we've got a lot of those. And we've got now a lot of CN minuses. And that's really important to have some more of the cyanide ions because we're going to use them below. All right, so how does this work? Well, if you drop in some base, and let's do a drop, and we drop in OH minus because that's our base. So we're going to drop the base into this beaker, and you can see that right here. The base is going to react with the what that's present? With the acid. And that makes sense that the acid and the base would find each other and react, and those are going to neutralize and form water and the cyanide ion. So the buffer is using its acid component to neutralize any additional base that you might throw at it. Now, what would happen if we were adding in, let's see, what other color do I have? Pink, there we go. Okay, so what if I added acid to the beaker instead of base? Well, what will happen is that the cyanide ion will go, hey, I am negatively charged, and I see that you're positively charged. And remember from the acid-base chapter, my friends, that chemists generally use hydronium and the H plus interchangeably. So don't be scared of that. We use those interchangeably. So the cyanide ion and the hydronium, or the H plus, they get together and they are going to neutralize, and you'll get water and you'll get HCN. So we're taking the acid molecule that we dropped in there and we're using it up. So it's not decreasing the pH, okay? So this is how the buffer system is neutralizing addition of acid or base. And remember, it can only handle a little bit, but it does handle it and it neutralizes it. So we're keeping the pH pretty much the same as it was before. Now, the next example is a weak base and the salt containing its conjugate acid. So we can have a weak acid and a salt containing its conjugate base, or a weak base and a salt containing its conjugate acid. So here we have our weak base. And when we put it in water, it's going to grab a hydrogen or H plus from the water, and it's going to make, not hydronium, excuse me, bad teacher, bad, ammonium, and it's going to make hydroxide. So what we have here, if we're looking at a beaker full of water, tons and tons of water molecules, is we have ammonia, and it's a weak base, so it will react a little bit, but not a whole lot. So what happens is it reacts with the water, and it's going to form ammonium and a little bit of hydroxide. Now, because ammonia is weak, it doesn't make a whole lot of ammonium, and we need to have the weak base and its conjugate acid. But since we don't have a lot of the conjugate acid, or enough to have a really good buffer, what we're going to do is we're going to put in a salt. Remember, the salt has a cation and an anion together. A salt containing the conjugate acid. So this is a conjugate acid right there, you guys. And the salt is very soluble in water. So the cation and the anion dissociate, or they ionize, they come apart. So this is very soluble. And so that's how we get an additional amount of ammonium ions. And we need those ammonium ions because we're going to use them down here to neutralize the base, okay? And that means that along with it comes the chloride ions. So let me switch the color on that one. Which one do you guys want? Let's do orange. We haven't done orange yet. Okay, so we're going to get some chloride ions in there too. All right, so what we're going to do is we're going to drop some acid in there. Oh wait, acid was pink on the last slide, so let's do pink again. Okay, so we're gonna drop some acid in there, and the acid is naturally gonna find what to react with? It's gonna find a base. And up here, we said that NH3 was the weak base that was in there. So ammonia gets together with the acid, and it's going to neutralize the acid, and it's going to make water and more ammonium, okay? Now remember, what is changing our pH is the presence of H plus or OH minus. So the H plus would cause a decrease in the pH, and an OH minus, a base, would cause an increase in the pH. So we're neutralizing the acid here by using the base that's already present. Now, what happens if we drop in some base? Okay, so that says OH minus. Okay, so the base is going to look for what in the system? It's going to look for an acid. And up here we said that we have this conjugate acid. We had a little bit of it when the base reacted with the water up there, but not much. So we threw ammonium chloride in there, so we would get a whole lot of that stuff. And now the OH minus is going to find the ammonium, the conjugate acid of ammonia. And remember, conjugate acids are acids. And they're going to react and they're going to neutralize that base there and give us water and ammonia. So the addition of acid is neutralized by ammonia, and the addition of base, that's neutralized by our ammonium. Okay, so again, that's keeping the pH pretty constant there when we have that system also. Now, what does this look like when we do a titration? So if you guys remember from the titration lecture, we took a look at the titration setup and what the curves looked like. So what we have here, and I'm going back to the weak acid in a salt containing its conjugate base example, okay? So what happens when we do a titration and we have a buffer system? So again, in the burette, we have base. And when you did your lab, you had a base of known concentration, and what you had down below was an acid of unknown concentration. And you guys titrated the base into the acid, and you use the indicator phenolphthalein, and it turned pink after you swirled it, and then you said, oh, that's wonderful, and you were done. But if you were to graph the pH change, what would it look like? Well, the graph of a titration is going to look a little bit different depending on what you're doing. So the first example here, this is a titration of a strong acid with a strong base. And what we're doing is we're reading the pH of the stuff that's in there. So imagine having a little pH meter, and it's got its little probe in there, and it's giving you a little value right there, okay? So we're going to start out with a very low pH. This is a strong acid, so we're starting at about 0, and you're dripping base in there. So slowly this pH is going to rise until you use up all of the acid that's in there. So your base, as it's dripping in, it's reacting with the acid. And once you use all of the acid up and you're still dropping base in there, you're going to get an immediate rise in your pH because you don't have any acid to neutralize it anymore. You're just putting base in there, so your pH shoots way up. If you are titrating a weak acid, with a strong base, what happens is that your weak acid naturally sets up a buffer system in there. And what we will see when we graph this is we'll see a different region over here. It looks very different from the titration of a strong acid with a strong base because you can see something's going on with the pH in that region. You don't have the rise that you had in the strong acid and strong base graph. This is called the buffer region or the buffer zone or the buffering zone. And if you guys go on to general chemistry and beyond, you will see a lot of these graphs, and you'll see graphs for polyprotic acids that have a number of different rises, and it gets really interesting. So that's what the titration looks like when you have a buffer zone. All right, so if we have a base in our beaker, our Erlenmeyer flask here. So let's cross out acid. We've got a base down here, okay? This is not what you guys did in the lab, but what if you did this? What if you had acid up here and you had base down in your Erlenmeyer flask? So we've got acid up here. And again, we've got a pH probe down in here. And your little pH meter is giving you a readout. So what it's going to start at is it's going to start out at a high pH up here because it's reading the pH of a base, and bases have higher pHs. So what we're looking at in the first graph there is a titration of a strong base with a strong acid. And what you see in the first part is you see that the base is reacting with the acid that we're dropping in there. And the pH is staying pretty high as long as you have more base than you have acid. And right down here, you're starting to use up all of the base. And once the base is all used up and you're still dropping acid down into the Erlenmeyer flask, the pH is going to take a dump immediately. It's going to go bam, and it's going to go down because then you have excess acid, and that's going to drop the pH. If you have a titration of a weak base, with a strong acid, what you'll see is a titration curve that looks a little bit different from the first one. And you guys might recognize that it looks like an upside down version of this one right here. And you might also notice that you have some strange going-ons over here where the pH is changing. So it looks different from the graph above. And again, that's going to be your buffer region. So that's just what it looks like in graph form. Now, there's one more thing about the two different types of buffers that I want to point out to you guys. And that is this guy right here. So notice how our salt gave us sodium, the sodium ion and the cyanide ion, and then we went on to talk about what the cyanide ion does, and we didn't say anything more about the sodium ion floating around in there. Well, the sodium ion doesn't do anything, so that's why we didn't mention it. It just keeps on floating around in the water, and it just kind of observes, it just watches what everybody else is doing. It's like, I'm good by myself, you guys go party, I'll just watch what you're doing. And when we have these ions that just hang out and watch what everybody else does but don't take part, we call them spectator ions. Spectator. Is that an ER or an OR? Spectator. Spectator ions. I am a terrible speller. I passed advanced calculus with an A, but I cannot spell to save my life. Okay, spectator, I think it is. All right, spectator ions. Also, if we take a look at example number 2, the spectator ion there is the chloride ion. It's an anion. It hangs out and it doesn't do anything. It just watches what everybody else is doing. So we have an ion that just spectates. Okay, so now that you've heard the term spectator ion and you know what it is, you're ready to go on to Gen Chem and hear about it again. Okay, so we were talking about blood's buffering system, and then we said we have to talk about what a buffer is, first of all, before we can talk about blood's buffering system and why this is important. Well, here we are. Okay, So, blood's buffering system involves carbonic acid. That's that guy right there. And its conjugate base, bicarbonate. Excuse me. This is also called hydrogen carbonate. I don't often hear people call it hydrogen carbonate. I hear bicarbonate more often. But this is the acid right here. And this is the conjugate base right there. So those are the main components of the blood's buffering system. Now, what happens when we have addition of acid to the system? And this is really important because it's very important that our blood does not get too acidic or too basic because we can die. Well, when we have addition of acid to our system, the conjugate base here in the bicarbonate system says, I am the hero, and because I am a base, I will take care of the acid and I will neutralize it. So bicarbonate reacts with the acid, neutralizes it to form water and carbonic acid. Now, if you add base to the system, the acid portion of the blood's buffering system, carbonic acid, it says, I am the acid, and my purpose in life is to react with the base. And so it does that. And it neutralizes it, and it forms water, and it forms bicarbonate. So that's how the blood is handling minor shifts in the pH, and it's extremely important. So here is the slide that we just looked at. And I shortened it a little bit to fit it onto the slide. But if you need the plus H2O, you can go ahead and write it in on this side. Or you can go, okay, it says AQ, so I know that these things are floating around in some water and an H2O is available. All right, so what happens when we exercise is that we have a buildup of lactic acid that happens. And so what we're getting is a lot of this right here. So we get a lot of this right here going, hello, acid, because it's the conjugate base of carbonic acid. I will react with you, and that's that plus sign, and we will go in this direction to make this. So you guys can see here that a dump of acid is being taken care of by the conjugate base bicarbonate right there. It's going this way. It's making carbonic acid. And we need to get rid of the carbonic acid. So what happens is chemistry to the rescue, and carbonic acid breaks down into CO2 and water. And when you're exercising, how do you get rid of that excess CO2 and water that you have because you're moving so much? Well, you breathe the CO2 out, and what do you do with the water? You sweat it out, and then after you've done your 5-mile run, you're like, oh my goodness, I've got to pee. And you get that out some more. Okay, so that's what's happening there, but what happens if it breaks down the system? Well, if our system fails, or if we have acid or base that's overwhelming our buffer system, and the blood pH gets lower than 7.2, this results in something called acidosis. And this can kill people, and this happens often in severe diabetics. If your blood pH gets above 7.5, we're going a lot more basic than we need to, or a lot more alkaline than we need to. This is called alkalosis. This can also kill you. A symptom of alkalosis is hiccups. Now, what acidosis and alkalosis look like in a clinical setting, I will leave that to the nursing program or your medical program, or at least the biology class that you're taking after this, because we are now done with the simple buffers lesson. Okay, bye bye.